Alright, so today I'm going to do a video on Blaise Pascal and actually mostly just like Pascal's triangle just because that stuff is cool. Um, what exactly to start on? So Blaise Pascal was a Frenchman from 1623 to 1662. Can't read that, I just read it for you. And he had a lot of impact on mathematics, a bit on physics and like water pressures, and also he was popular uh, in the world of theology, so religion. And we're not going to go into much of that. Either way, so we name him after a triangle that you can make, and I'm not going to go into the triangle just yet. We're going to go into a bit of a puzzle that can be solved using his triangle. By the way, it's not his triangle really, it's more just like we just like to call it Pascal's triangle in the West. Really, it's existed for like millennia. Let's just start with a simple 4x4 grid. That's not perfect squares, but I don't think I'm here to make perfect squares. So the question is, using only movements of right or down, you can mix it up in any order. How many paths does it take to get from here to, let's put an F for finish here. So how many paths to get to F? And I recommend you try this on your own, pause the video, I don't know, your choice. And I'll go into it in 5, 4, 3, 2, that's not even seconds, but 1, 0. Alright, so the trick here is, it's kind of weird, but so using only left, down, and right movements to get to F, how many paths are there? And so one path would be like here, to here, to here, to here, to here, to here. That's one. And you can just keep counting all of these. That's kind of a waste of time. So the trick here is to start small. So how many ways are there to get to this space right here? So you can only make like a right move from this starting space. So there's one here. Here, the same logic applies. It's just you can only make one down movement. Here, you can only go down. You can't go backwards. That's not one of the movements possible. So only one here, only one here. Only one here, only one here. Now let's continue this. How many to get here? You can actually count them. One is go here and down here. One is go here and then go over here. So that's 2. If you notice, that's technically just adding these. 1 plus 1 is 2. And you probably won't see Pascal's triangle just yet, but if you already see it, that's pretty cool. Let's continue. So 1 plus 2 is 3. There's 3 movements. You can count them. 1, 2, 3. That's 3 movements. This one, there's 4. You can just add them. Yeah, let's just use this adding rule. That's easiest. So 2 plus 1, 3. 3 plus 1 is 4. Now, how many get here? That's 1, 2, 3, 4, 5. So there's 3 to get here and 3 to get here. So I'm going to guess there's 6. Just add these 2 squares together to get this one. Let's do the same one for this. So 6 plus 4 is 10. 6 plus 4 is 10. And now we can reach our answer. 10 plus 10 is 20. There are 20 paths to get to F. And you can expand this to 5x5 grids. This puzzle exists in many forms. But this is a general one that's pretty straightforward. But it's an interesting application. And all we have to do to make it Pascal's triangle, I mean, he actually drew it in this grid fashion, but most times we draw it like a triangle reading this way. And here I probably have space right here to draw it. So you start 1, and you just have 1s on the sides. And we'll go into its uses and other ways you can make this without just adding in a sec. So 1 plus 1, 2. You just add the consecutive. 3, 3, 4, 4, and 3 plus 3, 6. Let's do one more row. That's 5, that's 10, that's 10, and that is 5. So you can see there's actually this kind of symmetry going on down the middle. I should change colors so I don't overlap colors. But either way, so 20 would technically be right here if you turned this sideways, which is kind of weird to think about. But you kind of have a grid going on if you think about it in this style. I'm going to destroy my beautiful drawing of Pascal. But you make these risks when you make videos. Anyway, so you can kind of see this going on. And you can see it both ways. In fact, some people prefer this one. I think this one makes almost a little more sense. This one works as well. We'll see how we can use them in a sec. Either way, and by the way, this has been this triangle fashion and its uses has been used for centuries before Pascal. It's just Pascal is he's kind of one of the first guys to even introduce probability theory, and this can actually be useful in combinatorics. And let's continue here. Move this sheet down. In here. Alright. So why did I write that in the corner? We'll see in a second. So let's redraw that triangle just real fast. 1, 1, 1, 1, 1, 1, 1. In a sense, you can think you have zeros on the side and you're adding these together to get those ones. I don't know, whatever you want to think. That's 3, that's 3. Let's do one more row. 6, 4, 4. I guess you can keep doing that 0 thing. Alright, so here's the idea. This is the formula that generates these. And this is actually called, in a sense, choosing. It's n. The way you say this is n choose k. And to solve that, n choose k, you plug in this into this factorial, these factorials. Quick thing on factorials. Factorials are just, let's do an example. 5 factorial. All that means is it's shorthand for 5 times 4 times 3 times 2 times 1. 4 factorial. You probably already see the thing. 4 times 3 times 2 times 1. It's kind of a weird thing, and it actually increases really fast. So from 5 factorial is already like 20 times 6, so that's 120. This is 4 times 3, 12 times 2, 24. 10 factorial, I don't even want to calculate this, but just know it's a big number. So it's 10 times 9 times 8, whatever, keep going, times 3 times 2 times 1. All right, and let's take one other factorial that will be useful in using this formula. Yeah, I like using this as a joke to scream like 5. And this is, rather than calling it 4 factorial, that's like the factorial symbol. 4. Whatever. It's only fun in certain circles. And then 0 factorial. This one actually shows up a good bit. And how do we solve this? We just need a way to solve this so we can actually plug in zeros into this formula and get answers. So let's look at these results and stuff like that. Here, let's look at 2 factorial. 2 factorial is 2 times 1, which is 2. 1 factorial is 1. So how do we get to 0 factorial? So let's look at this. This 2 factorial equals 1 factorial times 1. That means that 1 factorial equals 0 factorial times 1. And is this a good sense? Oh wait, no, this would be times 2. Here, let's try to rewrite this. I'm really just throwing examples out here to try and find this. Now let's look at 3 factorial. 3 factorial is going to be 1 times 2 times 3. That's 6. All right, so to get from here, let's actually define it this way. So going down. So 2 factorial is the same as 3 factorial divided by, well, 3. And that works. So let's use that formula again. 1 factorial is equal to 2 factorial divided by 2. So just to check, 2 factorial is 2 equals 6 divided by 3. Yep, that's true. and 1 factorial is 1, and 2 factorial is 2 over 2, that's 1, yep. So that means 0 factorial, this is interesting, is 1 factorial over 1. 1 factorial is 1. 1 over 1 is the same thing as 1. So 0 factorial is 1. All right, that's actually an easier result to work with, and it's actually nice. All right, let's see. So I'll just tell you this. So this is the setup. So all these ones have this pattern here. So this first thing up here is 0, choose 0. And we'll go over why it's choose in the first place. This would be, I'm pretty sure it's 1, choose 0. This is 2, choose 0. This is 3, choose 0. All right, and let's keep going with this. So this one over here would be 1, choose 1. This would be 2, choose 1. 2, choose 2. And you can try out what these results even are to see if they work out here. And 3, choose 1. Yeah, the majority of this video will probably be me writing these out. 2. And also it's tempting to write fractions here, but that's not how this notation works, this way of writing. 3, choose 3. All right, so 0, choose 0. Let's plug in this formula. So 0 over 0, so plug in 0, factorial, 0 minus 0, take the factorial of that, 0 factorial. Well, all of these are 1. So 1 over 1 is just 1. So 1 goes in that first space, checks out. Let's do 1, choose 0. 1 factorial, that's just 1. 1 minus 0, 0 factorial. That's a factorial here. And we put parentheses just so we know that we're taking factorial after we subtract these. All right, that becomes 1 factorial, which is 1. That's 1. That's 1. 1 over 1 is 1. Yep, that checks out. And let's try one more, and then let's move into the center, because we know all these should be 1 on the side. And that actually tells you something interesting, that if we ever have the setup n over n, I didn't mean to do fractions, then it's always going to be 1. That's interesting. And the other interesting thing is if it's ever over 0, it will always be 1, just from looking at this pattern. And yeah, we probably don't need to do 1, choose 1 to show you that. So 2, choose 1, we should get the result 2. After we do this, I'll just move on. This is just getting the idea down. So 2 factorial over 2 minus 1 factorial times 1 factorial. So that's 1, and this is 2 minus 1, 1. 1 factorial is 1, 2 factorial is 2. So we have 2 divided by 1 times 1, 2 divided by 1, which is equal to 2. Yep, that checks out. And one last one. 3 over 2. No, you get the idea. So all of these correspond to these. And this formula is actually nice, because what if I told you we were like on the 100th row? Then if we're on the 100th row, we'll know we'll have to do 100. And if there's a 0 place, first, second, third place. So if I was at maybe like 50, rather than actually go through this process of adding all throughout here to get 100, choose 50, we can actually just use this formula, plug it in. Now, of course, that'd be 100 factorial. 100 factorial is 100 times 99 times 98 times 97. Either way, a massive number that would be hard to write on paper. So this is just an example to show that this process is a nice formula to do this. Either way, so where next? All right, so why is it called choose? So combinatorics. So that is, actually it sounds exactly what it is. If you have 2 items and you're choosing 1 out of them, so that's 2 items, how many combinations can you have of that 1? Well, 1 combination would be this, and the other would be that. There's 2. 2 choose 1 is 2, so that checks out. All right, let's do another. Looks like glasses. Nice. Why did I do that? Either way, let's do more. So now we have, let's move on to the 4th row. So this would be choose 0, choose 1, choose 2, choose 3, 4, 4, 4, 4. I'm just writing their equivalent so you can see them firsthand. Alright, so let's do this scenario. 4, choose 3. So what this tells us is that if you have 4 items and you choose 3 of them, there's only 4 combinations of that. Let's look at here. And let's change colors. I'm doing a lot of this color. So this would be one combination of 3. This would be another combination of 3. This would be another combination of 3. And that formula tells us there should be one other combination. I think it's this one. Alright, yeah, that's 4 combinations. So either way, nice, because you can find combinations. Finding combinations is a huge part in probability, and so using this formula is helpful. And if you don't want to use the formula, you set up this table. If you don't want to use tables, use the formula. It goes both ways. It is nice for plugging in on the calculators. This is nice for just drawing out. And Pascal would have huge tables of this stuff just to calculate probabilities of combinations. So one other use of these, let's just go straight to it. So here I'm going to fold this, allow me to switch sheets. This takes a second. I need to get used to computer paper. There should be a way to fold this. Aha, there we go. See? I know what I'm doing. I'll put that under there so it doesn't bleed. Either way, let's just finish off with the last application. Well, there's still a ton out there. It's just, I like these. Alright, so let's just go right into it. So we understand factorials and all that stuff. Let's set up one more. That's 4, 6, 4, 1. Alright, so here is the final application, and it's going to seem weird, but here it is. A plus B to the N equals... I shouldn't write the complicated. Here's what the complicated formula looks like, but you're going to see that binomial thing. This just means sum. I'm just going to try and make this up on the fly. I'm probably going to mess up. And so I believe I goes here. And this is N. And this is until I equals N. And A to the N, B to the, I believe it's, let's see, I think that's I minus N, N minus I. This would be minus I. Alright, there we go. So this is our formula. It doesn't look like anything useful. I mean, really, like, what does this even mean? Either way, so let's actually do an example. So if you have 1 plus x squared, what this is saying is, let's plug it in, and we'll go over summation later, but this is the idea. I should, in fact, just start with an easy example than this. So that's n minus I over there. So n is 2. I is just a variable here. Oh, why did I write n? I meant to write 2. And then a to the n minus I. Let's change colors, just keep this thing going. A to the n minus I. N is 2 minus I. And b. By the way, a in this case is 1. I should just write that. 1. And b to the I. B is x. And we're taking that to the I power. So what this is saying is that if you expand this out, plug in 0 into all of this, anything choose 0 is 1. We know that. So it's going to be 1 times 1 to any power is just 1. That's also nice. That cancels out to 1. That cancels out to 1. And x to the first power. Am I right about that? Yeah. Oh, wait, no, to the 0 power. Anything in 0 power is 1. So the first result is 1. Then we're going to add that to the second one. Let's plug in 1 into all of this. 1 choose 1. 2 choose 1. So let's look at the second row. This would technically be the second row. By the way, this would be n equals 2, n equals 1, n equals 0. We like to start things with 0 in math. Let's keep going with this. Plus, I'm pretty sure. So 2 choose 1 is 2. That's always going to be 1, x to the first power. And the last one should just be x squared. You can plug this in. If you know how to work this, then nice. If you don't worry. And so let's also multiply this out. That's the same thing as 1 plus x, just see if we get the same result. All right, so FOIL, so those. So 1 times x plus 1 times x, that's 2 1 times x's, so that's 2x. You have 1 times 1. And then you have an x times x, that's an x squared. Check it out, it works out. Let's try it different. Let's not use this formula, just to keep it straightforward. And this video is starting to get a bit long, but this stuff is useful. Because if ever you have to multiply two numbers like this, it's called a binomial. These are binomial coefficients. Just means the first term. You can see that 1, 2, technically there's a 1 here. 1, 2, technically there's a 1 here. How about this? 1 plus 3 cubed. Alright, technically that's the same thing as 4 cubed. So if you just solve that, 4 times 4 is 16. 16 times 4 is 64. So we know we should get 64. But let's use this idea. So we know this is going to be a result. So the first thing will be a, if you don't follow along, don't worry, I'll go over binomial coefficients a little more later. I just want to get this over with. So our first term is 1, so it'll be 1 to the third power times first thing is 1 there, times 3 to the 0 power, plus 1 to the second power times 3 times 3 to the first power. Alright. All I'm doing is, this basically is an exchange. It's one of these numbers is going to decrease from n to 0, and one of these numbers is going to increase from 0 to n. In this case, our n is 3. There's n equals 3 row again, if you didn't notice. 1 to the 1 power, that's a multiplication. We have 3, that's in that third spot. And times 3 squared. Then we're just going to add that to one other thing, which is 1 to the 0 power times 1, because 1 is right here, times 3 cubed. Let's see what we get. So 1 to the third power is just 1, and then 3 to 0 is 1. So nice. That's 1 times 3. 3 times 3 is 9. Plus, this better work out, 3 times, so 3 squared is 9. 9 times 3 is 27. Let's keep doing this. And 1 times 1, so 3 cubed, we just calculate that, that's 27. So we have two 27s. 1 plus 9 is 10, and 27 plus 27 is 40, 54. Let's add that, 10 plus 54, 64. Check it out, it works. Now, of course, this method is easier, but if we made that x, like if you made this x plus y cubed, this is the pattern. You'd have 1 x cubed plus, well, in this case, 3x squared. This is just this may look like it's taking me a bit to solve, but just try to make sure I don't make mistakes. Plus 1 y cubed. Technically, if you multiply this out all 3 times, it'd take you forever. Yet using this triangle, which can go on forever, you can calculate all of these things multiplied by each other really fast. And x and y can be anything. In fact, I should have just used this. Just figured out the formula and then plugged in 1 and 3. But we got the same result. Cool stuff. As Pascal's triangle. Pretty cool dude.